really going to take a look at modeling situations where things are growing in a way that we say is exponential, and kind of tying that into what we've seen so far with our notes over exponential functions and their graphs. So what I want to do is kind of work through some of these examples with you here, making sure that you're writing these down as we go, because you'll be using this to complete your own work. But let's take a look at some situations here where we can talk about exponential growth. Okay, so notice it says colony A has a population every hour. What's happening is these suckers are tripling. Okay, so I'm trying to highlight these here. Okay, so it says complete the following table to show how many bacteria there will be each hour for the first 5 hours after the first observation. And so you can see here we've got a relationship between time and then the number of bacteria. So the first place I want to start is just at time 0, which is kind of a crazy thing to say. But at time 0, we're going to call this the initial time. And initial or initially just kind of means when you started. And we always look at this as time 0. And so this 2 is going to represent our initial amount. You know, going forward, we're going to call this our principal amount, but for now we'll call this our initial amount. So let's say we're starting with these 2 bacteria here. We say it triples every hour. Well, 2 times a 3 here, that would give us a 6. And if we take that 6 times a 3, this is kind of an easy pattern. This would be 18. If we take 18 times a 3, I think we get 54. Take that times a 3. You can see that this is a section that's going to be really helpful to have a calculator sitting around in. And 3 times 162 here, that'd be 300 plus another 180 plus a 6. So 486 is if we take this times a 3, and you can check me on a calculator here, but 486. Okay, so you can see that even with starting with 2 bacteria, if these things are tripling every hour, then this thing has the potential to, after 5 hours, be really big already, okay? So when I say number 1, describe the pattern and the data points, as the number of hours increases by 1, what's happening to the bacteria colony here? What I would say is every time the time goes up by 1, let's see if this types here. We see that the amount of bacteria is being multiplied by 3. Okay, and so this kind of gives us a sense of what really goes on with exponential growth. Is this idea that it's continuous multiplication, okay, over and over and over again, as our input variable goes up by 1 every time. So let's try this again here. As our input variable goes up by 1, the amount of bacteria grows by a factor of 3, which basically means it gets multiplied by 3 every time. So one thing we're going to do is we're going to kind of borrow from our pattern here and say, okay, well, if this is true about the 5th hour, then how many would there be 6 hours after the first observation? And so what we're going to have to do is we're just going to take this 486 here, and we're going to triple it. Okay, so we're going to take it times 3. This is where I will get out my calculator, and I'll say 486 times 3. And I get 1458. So if there were a sixth column here, we would have 1458, I believe is what we just saw there. 1458 is the case here. And the way we got this is just we took the 5th hour and we multiplied it by another factor of 3 here. So in part 3 I asked, well, in general, what would be a rule that would allow us to find the amount of bacteria for 10 hours? So this idea of finding the amount of bacteria at 10 hours is kind of this idea that, well, I could extend my table out to the 6th, 7th, 8th, 9th, and 10th hour and keep tripling by 3. But generally speaking, how are we going to be able to find the total number of bacteria here for any given hour? And so when we say the 10th hour, I'm going to start to kind of look at this relationship here as kind of like this idea that what we were doing is we were really starting with 2 bacteria, and then we were tripling it every hour. And so if I was going to triple this for 10 hours, then I would get something that looks like this. 2 times 3 times 3 times 3 times 3 times 3. And I would need 5 more factors of 3 because there are 10 hours in between the initial amount and the 10th hour. So you could really see that this is easily abbreviated this way instead, 2 times 3 to the 10th. And it kind of gives you this sense of we're starting with something here. We're starting with 2 of something. And what we're doing is we're tripling it every hour. And we're doing this for 10 hours. So to look at like how big an amount like this might get, we say 2 times 3 to the 10th power. I suppose we would get, wow, 118098, so 118098 bacteria. And for our 15th hour here, we would say, generally speaking, we could say 2 times 3 to the 15th hour, because we're going to triple it, and we're going to do that 15 times. So how big would this be here? So what if I retype this and I change my 10 to a 15? We would get this very large value here, 28697. So 2, 8, 6, 9, 7, 814 bacteria. Okay, so one sense you should start to get is that these exponential functions tend to grow really, really quickly here. So what we're going to do is we're going to plot the x and y coordinates on the plane and label the correct variable on the correct axis here. So what we're going to do down here is we're going to put time. Excuse me, let's see if I can write on this here. We'll put time. Okay, and then here we're going to put amount. And the thing is, in terms of time and amount, we're going to start at time 0 and kind of go out to the right here, like maybe 6 hours. But in terms of amount, we're going to have to go up to at least like maybe 500 to capture the 5th hour here. So maybe we do this. We say, okay, well, this will be 1, this will be 2, 3, 4, and we'll call this one 5 here. And it'd be easy to label all these down here. And if we're going to 500, well, we say 1, 2, 3, 4. You know, maybe what we do is we make every 4 of these 100. And so our scale is going to be 25s. So this would be 200. 1, 2, 3, 4, 300. 1, 2, 3, 4, 400. And we want to make this one really well because we're going to make another one to go with it here very shortly. So putting these points on here, we know that at the initial hour, at 0 hours in, we had 2 bacteria. So what would this look like? So let's pick a good color here. We'll pick maybe like a darker burnt orange here. So 25 is here. Okay, so 2's got to be like way down here. And so you can see our initial value is also our y-intercept here. We said that after the first hour we had 6. So to go from 2 to 6, it would be kind of like still down here and not very high off the ground. But it would be 3 times as far off the ground as this. If you triple your 6, you get an 18. So 18 is still under 25, but it's a little bit higher and closer to 25 here. And then what we did was we got to the 3rd hour, which was 54. So during the 3rd hour, this is this hour right here, we're at 54. Here's 50 right here. So 54 is going to be a little bit higher above. And you start to see that this starts to pick up a little bit here. During the 4th hour, we have 162. So 4th hour, we're going to go up to 100, which is 4 notch marks. 150, 6 notch marks. 162 would live right around in here. And then for our last one here, we'll put on 5, 486. 5, 486. So that'd be 1, 2, 3, 4. That's 100. 1, 2, 3, 4. 200. 1, 2, 3, 4. 300. 1, 2, 3, 4. 400. 50. 75. 486 would be clear up here. Okay. So what you're seeing is a graph of this tabular relationship, this table here. And what you start to see is that as time goes by, the rate at which this, or the speed at which this is growing, speeds up. It actually starts to accelerate. So for number 6 here, I wanted to ask the question, do you think we should connect the dots? Why or why not? And so in terms of what's going on here, I want you to understand that this is just kind of a model. And in terms of a model, we know maybe that these 2 data points happen here, but did the data points happen in between? We can assume that because we're just using this as a model, that yes, we should kind of connect the points here and say that this is a continuous curve. I'm trying to get this to be as smooth as possible here. And that it gets steeper and steeper and steeper as we go to the right. Okay. So what you would see is this exponential growth function, like we've seen in our previous notes, that kind of goes left and right forever and ever, but gets, in this case, steeper and steeper as we go to the right. Okay. So what I want to do for the second part of this is we're going to switch up the situation and say, how would this have been different if we had started with not 2 bacteria but 3 bacteria? And how about if instead of tripling it, we doubled it? So that's the situation we're going to look at over here. As a matter of fact, we're not starting with 3 bacteria, we're starting with 12 bacteria. So let's consider a colony of 12 bacteria that doubles every hour. Complete the following table to show how many bacteria there will be every hour for the first 5 hours. So a little bit different situation this time. The 2 things that you see that I really care about here are what I started with and what I'm doing to it every time. And with respect to our rule, these kind of things showed up here, what I started with and what I'm doing to it is those 2 bodies right there. Well, as we look over here, we're starting with 12 of something, and what we're doing is we're doubling it every hour. So what that's going to look like is if we take this times 2, this would be a 24. If we take this times a 2, this would be a 48. If we take this times a 2 here, this would be a 96. Let's keep going here. 2 times 90 is 180 plus another 12, so 192. So we get 192. And this would be 16 shy of 400, so 384. 384 is what we would get here. Okay, so let's answer some questions here about this, and we'll talk about how this compares to the other situation. But it says, describe the pattern in the data points. How is this similar to the situation on the first page? Well, it's similar in that we're multiplying every amount each time to get the new amount. And how's it different? Well, we're not multiplying by the same thing. In our first table, we were tripling things every time, okay? And we started with 2 of something. Well, here we're starting with 6 times as many things, 6 times as many bacteria, but we're only doubling it every hour. Okay, so that's how it's different. How many bacteria will there be in 6 hours? Well, hey, how do we find this? Well, you just say you take your 5th hour, and what we're going to do is we're going to take that times another 2. So if we were to double this again here times a 2, we get 600, 760, 768 is what we would get here, okay? But in general, how would we write a rule that will allow us to find the amount after the 10th hour? So kind of like we did previously, we're going to look at this a little bit differently this time. We're going to look at this as, if I wanted to find during the 10th hour how many I have, well, I would say I started with 12 of something, but what I'm doing is I'm doubling it. So I'm doing this how many times? Well, for the 10th hour, I have to take it times 2 10 times. And for the 15th hour, I'm going to start with 12, and I'm going to take it times 2 15 times. Do you think these will be bigger or smaller than the values we found on the first page? And so, maybe form a hypothesis in your head here. We did start with more of something, 12 times 2 to the 10th. And let's see what we find out here. So we get 12288, so 12288 bacteria. And if we were to pull this back out and change this from 10 to 15 compoundings, this would be 15, we get 393216. So were these bigger or smaller than our initial values on this page here during the 10th and 15th hour? Well, they were smaller this time. And I'd like to ask why you think that happens. Well, the reason why is because our growth rate is just not as great. And so you can see that our multiplier is going to have the biggest impact on what we end up with eventually down the road. So here's what we're going to do. Using a different color than the one we used for the first graph, we're going to plot these data points on the same graphing grid. And then we're going to talk about which colony had the greater initial population and where that shows up, and then which colony has the faster rate and how that is evidenced in the situations here. So let's go graph these. It's going to look a little bit different this time, and maybe we'll do this in I like a purple for this one here, kind of a purple. So at the 0th hour, at the initial time, which was right here on the y-axis when x is equal to 0. We have 12, which is like 6 times as many as what we started with here. So it's kind of starting on top of this 0.2 that we had for the first graph. We have 0.12 here. And then it was 1 comma 24. Now 24 is right underneath 25, so we're still on top of the orange dots here. We end up with 2. 2 maps onto 48. So after 2 hours, we have 48 bacteria, which is just below 50. After 3 hours, we have 96 bacteria. So 3 hours, 96, well, this is going to put us at 50, 75, 100. So 96 would be about right in here. And then let's see here, at the 4th hour maps to 192. So 192, well shoot, 1, 2, 3, 4 would be 100, 1, 2, 3, 4 more would be 200, 192 then would live kind of in this neighborhood here. And then last but not least, we had 5 comma 384. So 5 comma 384, let's see, 5 comma 1, 2, 3, 100, 1, 2, 3, 200, 1, 2, 3, 300, 350, 375, 384 is right here. And so this interesting thing happens with these two graphs here. This pink graph, if we connect the dots, started higher off the ground. I'm going to have to do this in pieces, you guys. Started higher off the ground, or it had a greater initial value. But you can see that even though these are both exponential curves, that the orange curve was just simply growing more rapidly than the pink curve here. And that is evidenced by the fact that it was tripling every time and not doubling every time. Okay. So I say describe the relationship. What does the graph show us? What predictions can we make about the population of bacteria as time goes on? I predict that the population of bacteria is going to grow faster and faster and faster here. Okay. So which colony has the greater initial population? Colony A or colony B? Well, we mean to say colony B here has the greater initial population. It had 12 bacteria instead of 2 bacteria. So we say colony B. And how is this evidenced by the table or the graph? Well, looking at the table, it's pretty evident that at time 0 it had 6 times as many bacteria. But as far as the graph goes, it's evidenced by the fact that the second graph had a higher y-intercept than the first graph here. So our initial amount graphically is always kind of related to our y-intercept here. Question 12 says, which colony is growing at a faster rate, and how is this evidenced by the graph or the tables? Well, in terms of faster rate, you see our multiplier here is kind of our rate indicator. And so we can see it in the table as what we're multiplying by, and what we're multiplying by in the first table is just bigger than what we're multiplying by the second table. Tripling is bigger than doubling, okay? Now, how is this evidenced in the graph? Well, they both look like exponential growth curves, but the idea is going to be that you see that the orange curve gets steeper faster, so it has to have a higher growth rate, okay? So we've seen some exponential growth here and kind of a relationship between initial value and growth rate and how that relates to the graph here. So initial value is always our y-intercept and growth rate. You know, it kind of is indicative of how the curve is bending. Okay. What I want to look at now is kind of writing a rule. And it says compare the rules that we described in numbers 3 and 8 and then use them to write functions of the form y equals a times b to the x that describe the amount of bacteria y, so this is our amount of bacteria here, that exist x hours after the initial observation. And so this x variable is kind of like our time here. It is our time, guys. And then this is the amount at time, t. Okay, this y variable here. So could we write a function that would look like this? Well, colony A's rule would look like this. If you wanted to find the number of bacteria at any given time, it would be equal to y, and y is always going to be equal to this. Now, this is colony A. Let's go look at its rule. We said, generally speaking, we could write a rule for the nth hour, and that's something that, oops, I forgot to do here. But we would say, generally speaking, we started with 2 of something, and we were tripling it, and we were doing this every hour for x hours. So that's going to be our rule that we write here. And we see that we have, oops, we started with 2, and we're tripling it every hour for x hours. Whereas for colony B's rule, we're going to say the number of bacteria at any given time is equal to the 12 we started with, but we're going to double it every hour for x hours here. Okay? So it says for these situations that can be modeled by functions of the form y equals a times b to the x, tell what the values of a and b represent. And this is the big takeaway here, you guys. In terms of what a represents in both of these rules, a represents the initial amount. Okay? And we can look at this as going to be our y-intercept on the graph, or what we're starting with when time hasn't even begun yet. But that's what we're starting with. And as far as b goes, b is this base of our exponent here. We're going to refer to this as our growth. I'm going to put slash decay because we could decay. We'll see in the next example here. But this is our growth or decay factor. Remember, factor just means something we're multiplying by every time. Okay? So I kind of want to finish this up here by taking a look at a decay situation. We'll make this real simple for you. What if I were to put out 100 appetizers in the academy kitchen, and the amount of appetizers remaining is cut in half each hour after the initial observation? So what would this look like? Well, I still have time as my input variable, but this time it's not a number of bacteria, it's a number of appetizers. And what you can see here is this is still multiplication, but a little bit different this time. What you're going to see is I'm cutting this in half every time. So what I'm going to write is I'm multiplying by a half. And what I would end up with is 50 left over here. If I multiply this by another half, I would get 25. And then something really weird starts to happen. And I like this about these. Remember that these are just models and kind of predict what would happen. Well, you know what is going to happen next. If I take half of 25, I'm going to get 12 and a half appetizers, which is not normally the case. But then again, we're just modeling this. If I cut that in half, I get 6.25. And if I cut that in half, I get 3.125. So what's the pattern in the data points? How's this similar to the first two examples? Well, in this case, we continuously are multiplying by a decay factor here. So that's similar. We're multiplying by something, but it's different because we're multiplying by a number that is a fraction. Not 2 or 3, but something less than 1. So this is going to represent decay, and this is how it's a little bit different here. Okay. Number 16, how many appetizers will there be 6 hours after the first observation? Well, again, we're just going to take our 5th hour. We're going to multiply its data value by a half. And if I take that times a half, oh man, I think it's 3.125 times 0.5. We get 1.5625. 1.5625. Yikes. So we would get 1.5625 appetizers. We found this just by taking the 6th hour times a half to get the 5th hour times a half to get the 6th hour. So generally speaking, we'll say our 10th hour. In our 15th hour, how could we write these values here? Well, during the 10th hour, we would have said we started with 100 of something, but we keep taking it times 100, and we'll do this 10 times. And at the 15th hour, we would have started with 100, and we would have cut it in half, but we would have done this 15 times. Let's go take a look at some of the values we're getting here. So we say 100. In parentheses, we'll put 1 divided by 2. It's very common. And we'll say to the power of, we'll do this to the 10 first. Okay, so we get a very small value here, 0.0977-ish, 0.0977-ish, so approximately. And man, check this out. If we were to do this again and do it 15 hours later, not scientific notation, but not far from it, 0.03052, so 0.00352-ish. appetizers. So here's what we're going to do. Take a look at how decay is similar or different. Well, it's similar because we're always multiplying by a factor and always starting with an initial amount, but it's different because we're multiplying by a number less than 1. So we're going to plot our points here. Again, let's do this. Let's put time always on our x-axis here. Make sure I can write on this. Almost done, guys. So we're going to put time down here. And then we're going to put amount of appetizers, so apps here. And I think that because I started with 100 of something, it'd be really cool to make this really a good scale here. So we'll do our hours the same again. We have first, second, third, fourth, and fifth hour. Make this one a little bit bigger here. And if we're going to 100, man, what if we did this 5, 10, 15, 20, 25? I think we can make this fit. 2, 3, 4, 5. Here's 50. 1, 2, 3, 4, 5. This would be 75. Oh, and this will work. So that makes our top line 100 here, and our scale is going by 5s. Okay. So to graph this, well, what do we know? Well, we know we started with 100 of something. And remember that we're going to emphasize the fact that, and this is a really important fact, that our initial amount is always our y-intercept. So at 0 hours, we start with 100 of something, but after 1 hour, we have only 50 left. And after 2 hours, we only have 25 left. And after 3 hours, we have 12 and a half left, so that'd be 10 to 15, and about halfway in between. And then 6.25, well, 5, and 6.25 would be about right here. In the fifth hour, we had about 3 point something. That puts us right around here. So a little bit different to draw this time. I'm going to do my best here. We've got this curve that starts off decaying really rapidly at first, but what's happening to its slope from left to right, its rise over its run? Well, this is another graph that goes left and right forever and ever. But we see that it's starting to flatten out over time, and this is really evidence of decay. Okay, so it's becoming less and less over time. Some things, it never really quite gets to a height of 0. So according to this model, we can always cut something in half, but there's always something left. So this is a good time to remember that this never really approaches, or it approaches, but it never gets to the x-axis. And so we say that this has a horizontal asymptote at y equals 0. What else? What else? Well, I suppose that we could use this to predict how many appetizers would be left at any given time here. So as far as what our rule would be, say write a function of the form y equals a times b to the x that describes the amount of appetizers y that exist x hours after the initial observation. Well, the number of appetizers at any given time would be equal to the 100 I started with, but then it would be taken times a half every hour for x hours. So on number 21 here, I say if this pattern is to continue, will there ever be a time at which there are 0 appetizers remaining? Why or why not? And the quick answer is no. But the reason why is because whenever you take something that's not 0, something, and you multiply it by a fraction, there's always going to be something left over. Okay. So as we talk on Tuesday, we're going to look at some ideas behind growth and decay modeling, and we're going to formalize that then. Cheers.